Hi everyone, my name is Levente Chikor and the talk I'm going to give you is the final episode of the Discrepancy of the MegaFlow Cache series. As we all know, OVS implements a multi-layered cache architecture in its fast path. While at the exact match cache, as its name suggests, flows are cached by hashing their whole packet headers as they appear, in the MegaFlow Cache arbitrary bitwise wildcarding is allowed. This requires a more complex data structure and packet classification algorithm. In the MFC, therefore, we had the tuple spacer scheme as a packet classification algorithm, wherein entries matching on the same header bits are collected into tuples identified by the mass header bits. Within the tuple, the lookup is fast. However, the algorithm has to search all tuples sequentially until a match is found. So in a nutshell, a packet comes in, we apply a mask, look up in the corresponding tuple, and if header is found, we stop and carry out the associated actions, save, forward, or drop. Otherwise, take the next mask and continue the lookup process. If there is no match at all, packet will be classified in the slow path, and the corresponding tuple will be spawned in the MFC for future packets. Take a look at this oversimplified example where the flow table only has one allow rule on the TCP destination port 80, and every other packet should be dropped. On the bottom, all possible tuples are shown with respect to this flow table. When a packet with destination port 80 is received, we find a match in the third step. However, for the second packet with a different destination port, the algorithm had to check all the 16 tuples. So clearly, if the tuple space somehow becomes huge, we are in trouble. The discrepancy we revealed in the previous episodes is that for each flow table there exists an easy-to-craft packet sequence when sent to OVS will inflate the tuple space to a certain extent that for classifying each packet the algorithm requires an affordable long time, eventually leading to denial of service for all workloads connected to the same OVS. The particularly interesting aspect of the packet sequence is that it looks completely legit on the wires without any explicit traffic patterns, therefore it is non-trivial to detect or even mitigate it. Furthermore, since almost every packet spawns a new tuple and they last at least 10 seconds, the attack itself is very low risk. As my presentation's title suggested, we have been dealing with this problem for a couple of years. Every time we get rid of some limitations or variables we have fixed before. During the discussions of my previous talks, it turned out that OVS, when installed via the underlying system's packet manager, its kernel data path, aka the fast path, is shipped by the underlying kernel. This means that the kernel module itself is maintained by the kernel developers and is not necessarily in line with the mainstream OVS data path developed by the OVS developers. For instance, the former, as the kernel networking developers are not in favor of heavy caching, does not have the EMC, it only has the MFC. Furthermore, last time it also turned out that the DPDK-based OVS might be also vulnerable since both the pure and the DPDK version essentially share the same code base. So in its final episode, we released the less variable in our equations and scrutinized the different versions of OVS. For the evaluations, we use a simplified KVM environment. We have two servers, each running an OVS as its hypervisor switch. Within and between the VMs, we use a simple IPv3 session to indicate the performance of OVS. The attacker resides outside of the system and sends her malicious traffic trace towards the ACL installed on server 1. According to the ACL, around 9,000 tuples can be generated in the MFC. Every time the attack starts at the 20 seconds with 1000 packet per sec rate. If not stated otherwise, OVS is restricted to use one core only. Let's see first the case of OVS kernel. This is a setup we also evaluated previously. The only difference is that OVS here is more up to date. We observe nothing new here. As soon as the attack starts and the MFC becomes populated, the throughput quickly drops down to 0. Let's see now OVS source, the version compiled manually and having the EMC definitely switched on. This was the most controversial experiment we observed and we are really open to discuss this later on. First of all, we can see that the performance goes up and down during the attack. If there was only one valley in the beginning, and the case was totally fine as the malicious traffic seen first is going through the slow path, then cached in the MFC, and due to the number of packets, all of them can actually be cached in the EMC. This would disable the need for the TSS algorithm and the MFC afterwards. However, the pattern shows like while the malicious traffic populates the EMC, right after processing it, some other benign traffic evicts all previous entries from the EMC, requiring the malicious trace to be processed in the MFC. We verify this behavior by practically spawning two new VMs in the system and replay a different traffic trace much faster between them to populate the EMC. We have seen the same behavior, so there should be something else in the background. Anyway, we tried to simply increase the traffic rate until we observed what we expected. The rate was found at 4000 PPS, where the performance of a single core OVS drops down to 0. Note this attack rate is still somewhere around 2.5 megabits per sec, which is still very early. Finally, let's see DPDK. First, there is a slightly worse baseline performance due to the fact that we're still using IPER for consistency, which does not benefit from DPDK but requires context switches. On the other hand, the most important observation is that the performance resurges after some time, not back to the baseline, but still, and this is the phenomenon we are going to explore. In 2016, there was a patch for OVS-DPDK which introduces a ranking in the tuple space. This means that tuples having more hits will be ranked higher and the linear search process will find a matching entry faster. This, in our case, also means that the malicious traffic will never be found first and it requires more time to be classified. As a result, the overall packet performance is still affected, but the benign traffic can at least go through. In order to defeat the ranking, there are two key aspects we need to keep in mind. First, the linear search process itself starts from the end of the tuple space. This is also highlighted in the source code comments. Second, a tuple when inserted, it is appended to the end of the tuple space. This means that it will be ranked the highest as the linear search process will start the lookup at this tuple. So the overall performance of OVS-DPDK depends on the ranks, the number of masks, and the attack rate. So the main idea to defeat the ranking is to keep it busy all the time. We can achieve this by carefully stopping the malicious traffic trace to let some older tuples expire and hence disappear from the tuple space. Then we resend the traffic trace to respawn these tuples again, which by the insertion algorithm will be again placed at the end of the tuple space where the linear search process starts. By means of this, the benign traffic will never get ranked high and we still maintain thousands of tuples in the MFC. To reach this end, we can run the attack for say 10 seconds and then pause it for 2 seconds. This number can be optimized according to the use case, but for this short talk I won't cover the details. So this setting would mean that during the 2 seconds of pause time, the firstly spawned 2000 tuples will expire. We still have around 8000 active tuples in the MFC, while after the pause period, we respawn the 2000 tuples again. And we continue this pattern, which results in that the benign throughput can never resurge and a complete denial of service is achieved. Let's see what happens if OVS-DPDK can scale up to multiple cores. We observe that the previous method does not work, even if we increase the attack rate tenfold. So simply increasing the attack rate is not sufficient, and it eventually leads to the original TSC attack, as by faster looping through the traffic trace, we don't let any tuple expire. So what can we do then? The idea is then to not only increase the attack rate but also send each packet multiple times. Then, by maintaining a higher attack rate, our tuple generation rate can be the same as before, resulting in that tuples can expire and respawn. As a result, we need 3000 PPS and each packet to be repeated 3 times to beat OVS-DPDK on 2 cores. As the cores increase, we also need to linearly increase our attack vector. In other words, we need 6000 PPS and 6 packet repetitions and 12,000 PPS with 12 packet repetitions to beat OVS on 3 and 4 cores respectively. We can see that when the attack is on, the throughput of the benign flow is 0 and there are spikes during the pause periods. Since the benign throughput never resurges for a longer period the attacker is not in control of, we consider TSC 2.1 successful. Thank you for having me for the 3rd time. If you are interested in a more detailed study, please refer to our ArcSight paper. Thank you.